Welcome everybody. So this is the course about ideal classes and abelian varieties over finite fields. The goal of this course is to give an effective method to compute abelian varieties defined over a finite field, as the title suggests, in terms of fractional ideals, which is, so we want to compute a pretty geometric object in terms of something that is quite algebraic, or maybe let's say coming from number theory. The program of this course is that we're gonna have two parts which are quite separate from each other, but they will tie together very nicely in the end. In the first part, we're gonna focus about ideal classes, so fractional ideals, orders, and very number theoretical topics, and how to compute these classes, these isomorphism classes of ideals. While in the second part, we're gonna focus on the geometry and how to compute the abelian varieties. To compute these abelian varieties, we are going to need some restrictions. But we are going to discuss these restrictions more later. And for ideal classes, on the other hand, we are going to do something quite general. So typically when people talk about ideal classes, they only focus on the invertible ones, while we will also consider the non-invertible ones. And I'm going to teach you how to compute them. The style of the presentation will be a bit different from part 1 and part 2. In part 1 we are going to go very slow, give a lot of details, a lot of proofs, a lot of examples, while in part 2 some of the machinery will be given as a black box. So the proofs are either too big or too involved to be discussed in detail, so we are just going to give some ideas and some sketches for that. Together with the course, there are some suggested exercises. I will try to remember during the presentation, during the lectures, to point them out, but they are all going to be collected in any case on a PDF that will be given together with the course, with the videos. References for part 1, well, I wrote a paper about that, and I guess that will be the main source. There is a lot of references also mentioned inside, so you're welcome to check it out. And for part 2, well, we're going to see them later, so let's not worry about it now. Okay, I think we are ready to start. So as I said, in part 1 we are going to talk about ideal classes. But before even telling you what is an ideal, I want to tell you where these ideals are going to live in. So what is the universe? What is the container that contains them all? So in such a container are étale algebras over Q. Okay, let's start with the definition. An étale algebra over Q is a finite product of finite field extensions of the rational number. And such a finite field extension is also known or referred to as a number field. These are number fields. All right. Let me start by giving you an example how étale algebra usually look like. Example. So consider a polynomial f with the integer coefficient. And we also assume this polynomial to be monic, so the leading coefficient is equal to 1. Okay, we write the factorization into irreducibles of f. So and distinct, so the FIs are all different one from each other. And we consider the quotient of the polynomial ring in the variable, so Qx, modulo the ideal generated by f, by this polynomial f. Then we have that K, such a K, is an étale Q algebra, an étale algebra over Q. If and only if the exponents E1, E2, ER, up to ER, are all equal to 1. Okay? So in other words, such a K is an étale Q algebra if and only if the polynomial f is square free. Okay? Cool. Another example of an étale Q algebra is given by the product of number fields, and as we said, but we can take also the same number field. So in this case, we require the polynomials to be distinct, but we can also take the same number field and take powers of it, let's say. So something that looks like that. So take, let's say, small k, a number field. Then capital K equal to small k times itself is also an example of an étale algebra. Okay, so in particular, let me say also a few more words about these étale algebras. Remark. An étale algebra, so are commutative. So the product is commutative in étale algebras. If you take two elements and you multiply, let's say, A and B, you multiply A times B, then you're going to have also that this is equal to B times A. And they are reduced. And recall that reduce means that there are no non-zero nilpotents. Right? And let me just also introduce a little piece of notation that we are going to use later. Given an étale algebra K, we denote by K star, or K times, to be the set of elements, okay, that are invertible, so such that there exists an element y, also in K, with satisfying x times y equal to 1. Okay, so these are the units, and you can see that this is actually a group under multiplication. It's quite easy. Another way to see this K star is as the set of non-zero divisors. In K, or of K. So in particular, if K is a number field, let's say equal like the small k, then this set consists of all, or this group consists of all the non-zero elements of K, because in a number field, in a field, every non-zero element is invertible, so it will fall in here. But when you have distinct number fields and you take the product, then in set you have to remove more elements, not just 0. And I invite you to think about it. Take, in a simple example, take a number field, maybe multiply it with another one or with itself, and try to think about it, which elements, describe them explicitly, which elements are units and which elements are not units. Okay. Cool. So now we have these algebras, and within it we want to look at a particular class of subrings. And this class, these rings, these subrings, are called orders. So okay, K is going to be an étal algebra. A Q étal algebra. Now, definition. An order R in K is a subring which is also a lattice in K. That is free finitely generated Z module, so Abelian group, of maximal rank. In particular, what does it mean of maximal rank? So this maximal rank means simply that when you take the tensor product between R and Q, then you get the whole étal algebra K. Or, in other words, the rank as a Z module of R is equal to the dimension as a Q vector space of K. Okay? And another way to say the same thing is that K is the total ring of quotients, or the total quotient ring, of R. So more precisely, if we consider the multiplicative set curly S defined by the non-zero divisors in R, so take the units of K intersected with R, then we can recover K as the localization at this multiplicative set of R. Okay. Let me give you an example of what an order can look like. So if we take f with integer coefficients, monic, and square free, and we consider the étale algebra generated by this f, so polynomials with rational coefficients modulo the ideal generated by f, then the ring consisting of polynomials with integer coefficients modulo this ideal, the same ideal generated by f, is an order in K. And in particular, orders of this form that are quotient by a polynomial are also called monogenic or equation orders. Monogenic or equation orders. Equation order. And typically in this situation we use the following notation. So this étale algebra we are going to write to denote this étale algebra, we are just going to write Q alpha, where alpha is the class of X modulo the ideal generated by F. And similarly for the equation order, associated equation order, we write Z with square parentheses alpha. Okay? All right. So now I have a first small exercise / question for you. So f as before. We take a polynomial with integer coefficients, monic and square free. We write it as a product of distinct irreducible factors. So they are distinct by the assumption that the polynomial is square free. Then show that the étale algebra generated by f, so qx quotiented by the ideal generated by f, is isomorphic to the product of the étale algebras generated by the reducible factors. So qx modulo f1 times qx modulo f2 times qx modulo the last polynomial in the reducible factorization, fr. And now, so this is the first part of the exercise, and the second part of the exercise is actually a question. So, is it always true that the isomorphism that you have produced in the first part induces an isomorphism on the equation orders? Okay, so I invite you to either try to write down a proof and see if it breaks or not. So adapt the proof from the first part to the second case and see if it still works or it breaks, or to write down explicitly a counterexample where this thing doesn't work. Okay. Now let me give you a proposition. So K an étale algebra as usual. So let K be an étale algebra. A Q étale algebra. I might forget to write down or say that our étale algebras are Q, but we always consider them over Q. Now, first part of the proposition states that the set of orders in K, so the orders in K, admits a unique maximal element where maximality is with respect to the relation of inclusion. And we are going to denote this maximal element by OK. And the second part of the proposition states that if our étale algebra is a product of distinct number fields, or actually a product of number fields, any number fields, and these number fields are K1, we denote them by K1, K2, up to KR. Then the maximal order of the étale algebra K equals the product of the maximal orders. Yeah, where, as we just introduced a notation, we denote by OKI, the maximal order of the number field Ki. Okay, so the proof of this statement is left as an exercise. And let me give a name to this maximal element, to this exact maximal element, OK. Well, as I already said it here, so of the Radial algebra. Okay, so this concludes the part about orders. Okay, now we have discussed the rings that we are going to be interested in, and now we want to talk about a special kind of modules over these rings, which are a generalization of the concept of ideal of this ring, and they are called fractional ideals. Okay, as before, K is an Radial algebra over Q. And now we take R to be an order in K. Definition: a fractional R ideal is a sub-R module of K. So let's denote this sub-R module by the letter I. Sub-R module I of K, which is a lattice in K. Okay, so in particular, we have this set of elements of Ki, which is closed under multiplication by elements of R. It's an R module. So we have I times R is equal to I. And second, we have that I, when we change the coefficients from integers to Q, we get the whole algebra K. So when we extend the base of this free abelian group, of free finitely generated abelian group, we get the whole algebra K again. Observe one thing that is quite important, it is going to play a role later. Is that if I is a fractional R ideal, then the quotient R over I is finite. Has only finitely many elements. Okay? The reason being that both R and I are lattices in K. Oh, sorry. In order to form this quotient, we also need to assume that actually I sits inside R. So otherwise, this quotient doesn't make sense. Okay? lemma. Let's start studying some properties of these fractional ideals. So a regular ideal of I, so an ideal is a fractional ideal of R if and only if the intersection of I with the units inside K, so the non-zero divisors in K, is non-empty. So let me give you half of the proof, and the other one is left as an exercise. So we assume that this intersection is non-empty. So let D be an element which is a non-zero divisor in K and lies inside the fractional ideal I. Then we have that D times R is a subset of the fractional ideal I. And observe that no, okay. Yeah, so observe that we have this relation. And in particular, this tells you that the rank right. So, sorry, I is an ideal. And in particular, as a definition of ideal, this must live inside R. So this tells you that the rank of D times R is smaller or equal than the rank of I, which is smaller or equal than the rank of R. So the rank is an abelian group of D times R. It's smaller or equal than the rank of I, which is smaller or equal than the rank of the order R. And in particular, this tells you that these are all equal. These are all the same because D times R is clearly isomorphic as an R module to R. So in particular, they must have the same rank. And this tells you that I has maximal rank as an abelian group, and hence it is a lattice. Okay, and as I said, the converse of this the converse is left as an exercise. And as I said in the beginning, I invite you to check the PDF attached to the course for some hints, maybe. Okay. So this was the first lemma about our fractional ideals. Now, remark. Observe that if I is a fractional ideal, then there exists an element D, which is inside a fractional ideal, and it's also a non-zero divisor in K, such that the fractional ideal D times I, so consisting of all the elements of I times this element D, is a subset of R. So in other words, we can always find an element that pushes this fractional ideal inside the ring R. And also observe that this D times I is isomorphic as an R module to the original fractional ideal I. All right. So I think it's a good moment to give an example of fractional ideals. So consider the polynomial f equal to x cubed plus 10 times x squared minus 8. Polynomial of degree 3. It's monic, integer coefficients, and one can check that it's irreducible. We consider the Étale algebra generated by f, which in this case is actually a number field, because f is irreducible. And we're gonna use the notation introduced before, Q alpha. So let me just add one little comment about this notation. So when we have a number field, we use round parentheses. When K is just an Étale algebra, we use square parentheses. So it's a little difference, and but it serves to stress that the difference a little bit. Okay, between the two concepts. Now consider the monogenic order inside K. So the order generated by alpha, which is also, as I said before, the polynomials in X modulo the ideal F. This is an order in K as you've seen before. And you can also write this order as using, you can give us the basis. You can look at it as a free easy module. We know that it's a lattice, so you can write it as Z direct sum alpha of Z direct sum alpha square times Z, and the integers. And observe that we stop at alpha square because this is a polynomial of degree 3. So alpha cube can be written in terms of lower powers of alpha. Okay? So these two are the same. And now consider also the following lattice S, which I'm going to describe it as Z, direct sum with alpha Z, direct sum with alpha square divided by 2 Z. Okay? And I claim that this is an order in K as well. But you can also see it as a fractional ideal over R. A fractional R ideal, as we have seen. And one can compute that 2 times S is a subset of R. So I leave all the verifications of these statements, so that S is an order, that S is a fractional R ideal, and that 2 times S is inside R as an exercise. So they're all very easy calculations, but I really invite you to do them to get like some practice with them. Okay. So now we know what these fractional ideals are, and can we do some operations with these fractional ideals? So given two fractional ideals, are there ways to construct more fractional ideals out of them? The answer is yes, and in the following lemma we see some of these constructions. So take two fractional ideals I and j. Then the sum of I and j, the intersection of I and j, and also the product of I and j are all fractional ideals. Okay. Moreover, also there is a way to form quotients of like take some kind of division among these fractional ideals. So more precisely, we can consider what is usually called the colon ideal between I and j, denoted in this way, so with a parenthesis and a dot in the middle, which consists of the elements in K, in the algebra, in the big universe, big container of this fractional ideal, that sends j inside I by multiplication. And one can check that this is also a fractional ideal. And finally, there is also a notion of duality when you work with lattices, duality with respect to the trace. And this duality also sends fractional ideals into fractional ideals. So more precisely, we're going to consider the fractional ideal IT, which is going to be the trace dual of I, and consists of the elements of K, such that the trace of K over Q of x times I takes values in the integers. So a priori this will be rational numbers. So if you take an element of the fractional ideal I and you multiply by an element of x in the trace dual, you take the trace, you will get a rational number, and we take precisely the element x such that you get an integer z. And the claim of this lemma, the last claim in this lemma, is that this trace dual is also a fractional ideal. All right. So I invite you to check the exercise sheet because I'm going to say more about these colon ideals and this trace dual, and also I will give you some hints for how to prove this statement. Okay. Now let me introduce some notation. So we consider an order R, and we consider all the set of fractional ideals, fractional R ideals, and we're going to denote this set by curly I. Okay, And now observe one thing. So now that we have this set, we actually have some extra structure, some extra algebraic structure on it. In particular, one can observe that this I of R is a commutative monoid. With respect to ideal multiplication. So you take the map that takes a pair of two fractional R ideals and sends it to the product of them. This ideal generated by elements of I times elements of J. And the unit of this operation, so that turns this set into a monoid, you need a unit element in a monoid, is the ideal generated by 1, that is R itself. Indeed, since every fractional ideal is a module, we have that I times is an R module, we have that I times R is equal to I. So a priori, since it's a module, we know that we have an inclusion, but since R contains 1, then this inclusion is actually an equality. Okay. Definition. Now we're going to consider a special kind of fractional ideals. So an overorder of R is an order S in K that contains R, such that R is a subset of S. Okay, so observe that, for example, the maximal order of the Étale algebra is an overorder of R. And second, another way to construct overorders of a given order R is the following way. So for every fractional R ideal, so for every fractional R ideal I, the colon ideal I colon I is an order and actually an overorder of R. And it has a special name. This is called the multiplicator ring of I. Okay. Observe that, let me point out one thing, that if S is an overorder of R, then the set of fractional ideals of S naturally lives inside the set of fractional R ideal. Okay? So this means that every fractional S ideal has a natural structure of an R module, and this means that it's a fractional R module. Okay. And now let me give a lemma in which I'm gonna list a bunch of easy properties of fractional ideals. So in this lemma we're going to summarize a lot of properties that are useful to know. So in particular, the trace dual, the formation of the trace dual is an involution. So if you take the trace dual of the trace dual, you go back to the original ideal. If you have an inclusion between fractional ideals and then you dualize it, so taking trace dual reverses the inclusions. Okay. Also taking duals sends intersections into sums. Moreover, when we multiply by elements, the duality also inverts the elements. So, and of course, and here we want x to be a non-zero divisor of k. Otherwise, taking this division doesn't even make sense. Moreover, we have a nice relation between colon ideals and trace duals, namely that we can write the colon ideal I colon j as I trace dual times j, the whole thing trace dual. And from this it's not hard to deduce also that you can write I colon j as j trace dual colon I trace dual. And then the last one, which is also quite interesting, is that if you take a fractional ideal, you multiply it with its own trace dual, you get the trace dual of an overorder of R, and in particular this is equivalent to say that the multiplicator ring of the fractional ideal I is precisely equal to S. So maybe this is a good moment to stop 1 second and focus on this notion of multiplicator ring. So as I said, this is an overorder of R. And in particular, we see that the fractional ideal I can be considered as a fractional ideal over this order. And this is the biggest overorder of R for which I has a structure of a module over it. And this last step gives you a nice criterion how to compute this multiplicator ring. Actually, 2 nice criterions how to compute this multiplicator ring. Either as a colon ideal of I over itself or using these trace dual relations. Okay. let's move on. So let me say a few words before we keep writing. When we study the ring of integers, Z, we have numbers, we have these integer numbers, and the way we study them is to look at the prime factors of these numbers. So, like, 21 is equal to 7 times 3. These fractional ideals and fractional ideals inside order can be thought as a generalization of integers. So ideals are you should think of them as the integers of an order, and the fractional ideals are the rationals, like what they behave as rationals, so fractions of things. And now the question that this analogy should bring you to is, what are the prime elements in this case? What are the building blocks of these fractional ideals? And do they actually behave in the same way as for the integers themselves? All right. So in other words, what I wanted to say with this is that I want to talk about the concept of a prime of R. So for us, a prime of an order R is gonna be a maximal ideal of R. Okay. So let me give you a more precise characterization, because at the moment it seems that just we are giving a different name to something that we already have a name for. And so let's try to motivate why we call them prime. So prime ideals, the primes of R are precisely, so the maximal ideals are precisely the prime ideals of R. Which are fractional R ideals. Let me give you a proof of this statement. So let's give first the inclusion from right to left. So if P is a prime ideal and also a fractional R ideal, then the quotient R over P is a domain, is a finite integral domain. So it's an integral domain because P is a prime ideal, and it is finite because it is a fractional ideal. So as we've seen, when you quotient by two lattices, you get something finite. Okay, cool, but this means that it is a field. So every finite integral domain is a field. And this is the same as saying that P is also a maximal ideal. All right. Now let's do the other direction. So we take P, which is a prime of R, so a maximal ideal. so maximal ideal. Then when you take the intersection of P with the integers, you get a rational prime. So sorry, the ideal generated by a rational prime. Okay, and this, if you think a little bit about it, will show you that P must contain a non-zero divisor. In particular, the rational prime is a non-zero divisor inside K. And maybe if this step was a bit too quick, we have to maybe work with the thing that R is an integral extension of the integers. It's integral over Z. Yes. So every element of R satisfies a monic polynomial with integer coefficients. And in particular, this tells you that given a prime ideal of R, you get and you intersect it with Z, you get a prime ideal, and this prime ideal is maximal if and only if it is maximal when intersected with Z. Let me write it down. So given a prime ideal of R, then it is maximal if and only if the intersection with Z is maximal. And maximal ideals of the ring of integers are precisely ideas generated by a rational prime. Okay, this concludes the proof. Oh, it broke. All right. Now we introduce a new notion, so a new properties of that some of these fractional ideals satisfy, namely the notion of invertibility. Definition, so let I be a fractional ideal. So we used the notation that we introduced before, so curly A, fancy A of R. So such a fractional ideal is called invertible in R if there exists another fractional ideal J such that the product of the two is equal to the ideal generated by 1, so the order R itself. Such that I times J is equal to R. Okay, and let me first make a little observation. So if I is invertible, that is, such a J exists, then it must be equal to the colon ideal R colon I. Right? It plays the role of an inverse, so it actually makes sense if you think a little bit about it. The notation makes sense that j is going to be equal to r colon I. Okay? So now let me give you a quick lemma. Small property of invertible ideals. So lemma. Let I be a fractional ideal, and assume that I is invertible. So let invertible in R. Then the multiplicator ring of I is actually equal to R. Okay, let me give a proof. It's not hard, but it's good to see how to, in order how to get practice, like to get used to playing with fractional ideals. So since I is an R module, I is a fractional ideal. In particular, it is an R module. Then I times R is equal to I. Right? It's closed under multiplication by R. R contains 1, so actually we have an equality here. We already used this trick before. And this tells you that R is inside the colon ideal, the multiplicator ring of I. So remember, the colon ideal I over I colon I, consists of all the elements of K that sends I inside I. So in particular, this relation tells you that R sits inside this set. And now we want to prove that actually this is an equality. And to do so, we use the following trick. So consider the multiplication of I colon I. So the multiplicator ring of I times I. By definition, this is also equal to I, right? So this consists precisely of the elements that will send I inside I, and this contains obviously 1, so we get an equality. And now we multiply these relations on both sides by the inverse of I. So R colon I, right? We need to use this invertibility hypothesis somewhere, or at least we expect to use it, and indeed we're gonna. And we get so we get that I colon I times I times R colon I. This is going to be equal to I times R colon I, right? We are just multiplying this line by R colon I. And how we put things together? So here we have I times R colon I. I is invertible, so this multiplication is actually equal to R. Okay? And instead, on this other side, again, we put these two together by this exact same reasoning. We get R equal again. So these lines gives us I colon I. So the multiplicator ring of I times the order R is equal to R. And observe that this implies, so if you think a second, that we get that I colon I, since it contains R, is equal to R. And this concludes the proof. All right. So maybe it's a good moment to give an example. So we take the same order that we discussed already in the previous computational example. So let me write it again. So R is the monogenic order given by the polynomial x cubed plus 10x square minus 8. Okay, we denote by alpha is usually the class of x in this quotient. And we consider the same overorder that we considered before. So the one generated by 1, so as a Freezy module by 1, alpha, and alpha squared divided by 2. All right. So observe that these two are not equal. So there is a strict inclusion of R inside S. And I want also to think a little bit and try to figure out that the size of the quotient, so the index of R inside S, is actually precisely equal to 2. Okay. Now consider inside inside the K algebra the fractional ideal I generated as an R module, so a fractional ideal generated by over R by 3, the number 3, the rational number 3, and by alpha plus 2. Okay, so 3R plus alpha plus 2 plus times R. And I invite you to compute, or one can check. That the multiplicator ring of I is precisely equal to R, to the monogenic order R. One can also compute that the colon ideal, so the inverse, well, the colon ideal R over I is equal to the lattice given by, generated by 1 alpha and the element minus 1/3 minus 1/3 alpha plus 1/3 alpha square. And one can verify that I times R colon I is actually equal to R. So I is invertible. Now consider another ideal, J. This time given by the elements 1, so as a Freezy module 1, alpha divided by 2, and alpha squared divided by 2. Okay. And I invite you to compute that the multiplicator ring of J is equal to S. But on the other hand, J is not invertible in S. Indeed, when we take J times S colon J, then this one is not equal to S, but it has the multiplication, this product, and is index 2 inside S. So you don't get the whole order S, but you get something smaller. So in particular, J is not invertible in S. All right, this concludes the example. Okay. All right. Now, in what comes next, we are going to need to localize these orders, and we're going to discuss what happens to the notion of invertibility in relation with the localization. But as of now, we only define what a fractional ideal is invertible, so only for lattices. So now I'm going to give a slightly different definition of invertibility, and I'm going to show you actually, which is actually equivalent in the common case, in the common ground. So let me be more precise. So definition star. Let T be a ring, so any ring, not just an order. And I an ideal of T. Then we say that I is invertible in T. If there exists an ideal J, an ideal of T, J, ideal J of T, and a non-zero divisor let's say D inside T, such that the product ideal I times J is equal to D times T. Okay, and now, as I already anticipated, the definition that I gave in before is is equivalent to definition star for a fractional ideal, but this one has the advantage that allows us to work in more generality. So. All right. Okay. So now we're gonna localize. So okay. So I'm gonna state three lemmas. So lemma 1, so let T be a Noetherian ring then T is a principal ideal ring if and only if every maximal ideal of T is principal. Okay, so I'm not going to prove this lemma, but I'll give you a reference. So you can look in Kaplansky's book. And in section 12.3. Okay, lemma 2. So now let T be a semi-local ring. So remember that a local ring is a ring with a unique maximal ideal, and a semi-local ring is a ring with finitely many maximal ideal. And let I be an ideal in T. So T is a semi-local ring, I an ideal. Okay. Then I is invertible according to this definition star that we gave you. If and only if I is principal, so generated by a unique element, and the generator is a non-zero divisor. Right? The proof of lemma 2 can be found in Gilmer's book. This is proposition, appears proposition 7.4. Okay, and now another lemma, lemma 3. So now we go back to orders. So let R be an order in an étal algebra, okay? And I a fractional R ideal. Oh. Okay, and without loss of generality, well, let's assume that I is inside R, so it's included in R. then I is invertible in R. The fractional ideal I is invertible in R if and only if the localization of this fractional ideal at P is a principal RP ideal for every prime P of R. Okay. So in particular, this condition that I is inside R is necessary in order to make sense of this notion. We have not defined what is a fractional ideal of a localization, but a priori one can remove it just by multiplying by an appropriate non-zero divisor. On this one I'm going to prove, so let me give you a proof. So assume that so we start by assuming that I is invertible in R. Okay. In other words, we have that I times R colon I is equal to R. This is just a definition of invertibility. Right. Now we localize this relation. And we get that I localized at P times R colon I localized at P is equal to RP. Okay? And one can verify by just working out the definition that this localization is equal to the colon ideal of the localizations. Okay? Right, so we have this relation. Then we have that IP is invertible in RP. And moreover, by lemma 2, this implies by lemma 2 that IP is principal. And generated by a non-zero divisor. All right. Now we do the converse. We assume that IP is generated by a non-zero divisor. Yeah, observe, sorry, just let me add one thing to what I said before. Observe that this works for any prime P. So we have, this is independent of P. So this is true for every prime P. So IP is always going to be locally principal. Okay, as I said, conversely, let's assume that IP is principal for every prime P. So let's call this generator X. But let me stress that this generator depends on the prime. Okay, but there exists one generator for every P. So this is our assumption. And now consider the natural inclusion the natural inclusion of fractional ideals I times R colon I inside R. Alright? And we want to show that this inclusion is surjective at every prime P. And observe that in this case surjective means that actually we have an equality. Okay, and let's work it out. So we have that IP times RP colon IP is equal to XRP times RP colon XRP. Now we can simplify the X, the generator, in this relation, and we get, let me rewrite it, so we get X times RP times 1 over X RP times RP. So in other words, we can pull out the X from the relation, from the colon ideal. Now we simplify it, and we get that we have RP times RP colon RP, which is nothing but RP. Okay? So this inclusion I is surjective at every prime P, and being locally surjective at every prime, at every prime means it is also surjective globally. So inequality also globally. Okay. This concludes the proof, but let me give a corollary. Okay, so let R be an order as before, and let P be a prime of R. Then, so a prime P is invertible in R. If and only if the localization of R at P is a principal ideal ring. Okay, proof. So let's assume that P is invertible. Then by lemma 2, PRP, so the localization of the prime ideal, so the ideal generated by P in the localization, is a principal RP ideal. And this is the unique maximal ideal of the local ring RP, observe. And in particular, we have seen that this tells us that RP is a principal ideal ring. This was by lemma 1. Okay. Now conversely, let's assume that Rp is a principal ideal ring. Let me write it shortly as principal ideal ring PIR. Then, so there exists a unique generator, there exists a generator, single element that generates the unique maximal ideal. Let's call it X, for some X. Okay, and if Q is another prime ideal of R, so in particular where Q is a prime and we assume that it is different from P, then the localization of the prime ideal P at Q, so P R Q, so you look in the localization at Q and you consider the ideal generated by P is going to be the whole ring. So it contains one, contains a unit. And in particular, this implies that P is locally principal at every prime. Right, so at P we have seen that it has by assumption a unique generator, while when we localize at a different prime is the ideal generated by 1. So it's always generated by a single element. Okay, and then by lemma 3, we get that P is invertible in R. Okay. This concludes the proof of the corollary. And now I want to conclude with the last statement that says that, so what happens, so let's take an order R, and let's assume that every ideal is invertible. Every fractional R ideal is an invertible ideal. So can we say something more about this order R? And the answer is yes. And it turns out that the property that every ideal is invertible is a characterization of the maximal order of the étale algebra. So let me write it down. Corollary. So R is an order, and we have that every fractional R ideal is invertible in R, if and only if R is the maximal order. So R is equal to OK. All right, let's give a proof. So I'm first going to do the direction from top to bottom. So we assume that every fractional ideal is invertible. Okay? We have seen in our lemma before in the course that if an ideal I is invertible, if then the multiplicator ring of I is equal to the order itself. So if it is invertible in R, then I colon I is equal to R. All right, we apply it to a special ideal. So to the ideal that we denote by this, well, angry f, which is defined as the colon ideal of the order R over the maximal order. All right, and actually I want to just mention that this ideal has a special name. It's called the conductor of the order R. Okay. So first of all, observe that the multiplicator ring of this conductor is the maximal order, right? So proof, let me just prove it. Indeed, we have that f times the maximal order, by definition, sits inside R. So f consists precisely of the elements of K that sends the maximal order inside R. So we have this inclusion. But we can also write at the left-hand side of this inclusion as f OK times OK, right? And this implies that f OK is inside f, and this gives an equality. Okay. So sorry, this is actually an equality, and we conclude then that so the colon ideal f colon f is equal to R. We have this chain of equalities. All right, for the other direction, we are going to rely on some results from, well, number theory or commutative algebra if you prefer. So we will prove that every prime ideal P of OK is invertible. So we will prove it locally. All right, so we first write a data algebra K is a product of number fields. So K1 times K2 times KR with KI number fields. Okay. And we know that the maximal order, we have said it before, is equal to the product of the maximal orders. Okay. Now we pick a prime ideal of OK, so P of OK. And if you think a little bit about the definition of a prime, we know, we can see that there exists an index between 1 and R. This is an R. Such that the prime is equal to the maximal order everywhere else except at the ith entry, right? So if you look at the components, I mean, this ideal is going to be generated by 1 at every component but 1, where it is a prime ideal. All right. Now, by commutative algebra or maybe number theory, one knows that each of the maximal orders in this, each of the factors is a Dedekind domain. So it's the integral closure of the ring of integers of Z inside the number field Kr. And it is also a domain by assumption, so in particular it's a Dedekind domain. And this tells us that by, well, what one usually studies in number theory, that the prime Pi is invertible in OKI. In particular, we have that OKI is a discrete valuation ring whenever we localize it at any prime. And this is there are a series of equivalences. And this means that, so this fractional ideal is generated by 1 in every factor except 1 where we have a prime an invertible ideal. In other words, the whole P is invertible in OK. Right, and this concludes what I wanted to prove. And so every P is invertible, every maximal ideal is invertible, or by the lemmas that we've seen before, this means that it's principal, and this allows us to conclude that every fractional ideal is actually principal. So maybe I can write more about this. Every fractional ideal is invertible, sorry, I misspoke. So we have that the localization of the maximal order at P is a principal ideal ring. And this tells us that every fractional ideal we have that it is locally principal. So in particular, I is invertible. All right, this concludes the proof.